So we looked at Niels Bohr's work and how he came up with this model of the atom, where electrons can only exist at specific energy levels. Now, electrons can jump from one energy level to the next, but it's going to produce a change in energy. If an electron were to fall from this third energy level to this second energy level, well, now it's at a lower energy, and we know energy has to be conserved. So that change in energy, because of this equation using Planck's constant, that change in energy is going to produce a very specific frequency of light. If an electron were to jump from one level to the next, so it were to jump, it's going to have to actually absorb a certain amount of energy in order to jump up to a higher energy level. So electrons jumping are going to absorb energy. Electrons falling to lower energy levels are going to emit specific frequencies of light because they lose energy. Now, Bohr's model helps to understand why we see the different types of spectrum that we do. In spectroscopy, we take a source of light and we pass it through either a prism or a diffraction grating to filter and separate that light. Now, we have three different types. We have a continuous spectrum, which is every frequency of light present, and that's just pure white light. If we take a hot gas, we end up with an emission line spectrum. If we take white light and pass it through that same gas, but as a cold gas, we end up with an absorption line spectrum. Well, you'll notice the difference between an emission line spectrum and an absorption line spectrum is how these bands appear. In an emission line spectrum, we have just very specific bands appearing. So only certain frequencies of light are actually emitted from that hot gas. Whereas in an absorption line spectrum, we had a continuous spectrum, but now we're missing those specific frequencies of light. They've been absorbed by the cool gas. Now, a continuous spectrum is produced when substances are heated to a high temperature. Then they'll emit white light. So it sounds like black body radiation. Now, the important thing to note is how these colors will appear in the order they'll appear in based off of what we use to actually separate the different frequencies and the different wavelengths. So, for example, if we take white light and pass it through a prism, we know that red light is going to refract less than blue light because it has a longer wavelength, whereas opposed blue light has a shorter wavelength. So it's going to refract more. Different when we look at a diffraction grating, we know that longer wavelengths are going to actually diffract more. So longer wavelengths of light are going to diffract more. And we're going to end up with this pattern. Now again, depending on how good our diffraction grating is, we can end up with that pattern repeating over and over and over again. So this could be our first order on either side, and we could have a second order, third order, depending on how good of a diffraction grating that we actually have. But we can separate light using these two different apparatuses, using a prism, using a diffraction grating, and they'll determine which order that light will appear on the screen that we're looking at. Now, an emission spectrum happens when we excite a gas. A neon sign is an example of exciting a gas. We pass a high voltage through neon gas, and you have this orangish glow that you get from the sign. Now, that's not just one frequency of light that's hitting your eye. If we were to take that neon sign and pass it through a prism or pass it through a diffraction grating, we would end up with very specific frequencies of light being emitted. Now, those frequencies have to do with the electrons and the energy levels that are present in whatever element that we have, whatever the gas is that we're exciting. You'll notice in this Bohr energy level diagram that there's these holes. These are where the electrons originally were when they were excited. So if you were to excite electrons, they're going to jump up to very specific energy levels. So these were excited electrons. What happened, though, is that these electrons eventually fall back down to more stable states. Now, as these electrons fall, so they're excited and they become de-excited, they're going to lose energy. Now again, if we look at this equation, any change in energy is going to correspond with a specific change in frequency. If we have a big change in energy, we're going to produce higher frequency of light. So blue light is a high frequency. This energy change could correspond with the blue light that we see in the diagram. Whereas this energy change is very small, so we're going to have lower frequency of light being emitted. And then this energy change a little bit bigger, maybe a slightly higher frequency of light being emitted from there. Now you'll notice in this emission line spectrum we have more than just 3 energy changes. But this is kind of an example of what happens, what we need in order to produce an emission line spectrum, where these electrons are excited. As they fall back down, they're going to emit very specific frequencies. And those specific frequencies are what we see in that emission line spectrum. Now, that's different than an absorption spectrum, which is what happens when we take white light. So we have white light here. Now we can pass it through the same gas, but instead of exciting that gas, we take white light and we pass it through a cool gas. So this gas is originally in a de-excited state. And then we use a prism or we use a diffraction grating to actually separate that sample. So these electrons, you'll see where these dotted lines are, were originally in a de-excited state. As we pass white light through it, there's very specific frequencies of light that will cause energy changes in those electrons. So for an example, a higher frequency photon will cause that electron to jump up. A lower frequency photon will cause that one to jump up. And then maybe something a little higher than that will cause that one to jump up. So now those frequencies of light are absorbed in order to cause those electrons to jump from a lower level to a higher level. And that's how we end up with an absorption line spectrum. So we have these 3 different types of spectrum. There's a continuous spectrum, which is emitted from a light source. It's just pure white light, separated by a prism or a diffraction grating. We have an absorption spectrum, which results from electrons going from one level and jumping up. Now again, in order for those electrons to increase in energy, they need to absorb specific frequencies of light. In an emission line spectrum, we have an excited gas. As those electrons become de-excited, so they're originally excited, they fall down, they emit specific frequencies of light. Now, scientists had long known that when you heat up elements like hydrogen and helium, the light they emit come in very particular frequencies. Though to the naked eye, the sun spectrum seems to be continuous, if you actually view it through a prism combined with a telescope and a diffraction grating, it's easy to see that it isn't. This bottom pattern is what we get when we look at the sun. And you'll notice that this is an absorption spectrum. It looks like a continuous spectrum, but there's very specific bands of light that are missing. Now, what that tells us a lot about the atmosphere of the sun, and it also tells us a lot about the makeup of our own atmosphere, where the light being emitted from the sun is white light, but as it passes through the cooler atmosphere of the sun, now specific frequencies of light are absorbed. And we can use those absorption spectrums that we have from the sun and also other stars as well to determine the chemical makeup of that atmosphere and also of Earth's atmosphere, just based off of the different absorption spectrums that we have.